Hello. In this problem, we are going to find the electric field due to an infinite strip of charge. So the idea is we have a strip of charge of width L. Its thickness is very small. It's a very thin ribbon of charge, so to speak. With L, it goes on forever in either direction in that way. And we're trying to find the electric field, a height h above the center of this strip, or center of this ribbon. The charge per unit area of the strip is sigma. Sometimes the book uses the letter eta for charge per unit area. Some other books use sigma. So in this problem, we're using sigma. Let's see, how are we going to start this problem? Well, the approach, and this is the approach for nearly all problems where you have some configuration of charge and you want to find the electric field at some point. You divide up your charge into a bunch of little differential elements. Then you add up the field from each of those differential elements. So we're going to make a little square here that has if you see my coordinate system over there, this side is dx and this side is dy. So it's got it's a little square in the plane. It has one side is dx and one side is dy. It's a little differential element. So what we're going to do is we're going to cut the this ribbon up into a bunch of little squares. You can imagine like cutting it up like this into a whole bunch of little squares, so on and so forth. And we're going to find the field due to each of them. So here's an example little square. What is the field due to this little chunk? As is typically the case when you do this, you want to pick an arbitrary little square, not like the corner one. It helps if you pick like an arbitrary one and then label its position. So in this case, its position is, if we think of its position is here. Let's do this in red. And think of like a little triangle here to the location, this little differential element. This distance we're going to call x, and that distance we're going to call y. So what is the field due to this little charge element? Okay, so we'll do that. Before we get into a bunch of math, it helps to take a step back, look at the problem, and say, can we use symmetry to simplify this problem? And the answer is yes. We can find the field due to, we can see that the field due to this little chunk over here and a field due to a symmetric chunk over here would cancel out. So the chunk over here would create a field, which let's make field green over in that direction, and this guy over here would make a field pointing in that direction, and the horizontal components would cancel out. No matter which little square you have, there's a corresponding square on the other side of this point here, and their horizontal components will cancel out, so the net field in the end will be straight up. So what we can say is that by symmetry, Ex equals Ey equals 0. So I'm 2/3 of the way done solving this problem. I've already found 2 of the components of the electric field. Haven't found the third one. The third one's going to be the hardest to find, but I've got 2 of them already. Okay, so now let's work on the electric field due to, or electric field in the E in the Z direction. Okay, to do that, what I'm going to do is I'm going to use each of these little chunks in this ribbon and find the electric field due to each of them, and then integrate over the area of the ribbon. Okay, so first we need to find the electric field due to this little chunk. So if we draw, let's do another color, blue. If we draw this blue R, let me do this again. So that's the distance from our point of interest, where we're trying to find the electric field, and the little differential element. So this differential element is going to create some field here that points off in that direction. Maybe make it just a little bit bigger, actually. So that'll be pointing off in that direction. So we're going to call that DE, the DE vector. Okay, so we want to find the DE due to this little element here. Okay, to find that, we can use Coulomb's law. We can say that dE vector is equal to dq, where dq is, so that little charge there is dq, over 4 pi epsilon naught r squared, where r is the distance, this blue distance here. Okay, what is dq? Well, dq, we are told that the charge, we have sigma charge per unit area, so dq is the little d area, the area of that little square, times sigma. Well, the area of that little square is dx dy times sigma. So because in x on one side, y on the other side, area of a square is, or area of rectangle is the height times the width, so dx times dy is the area times the charge per unit area gives you the little differential charge of that little segment. So we can rewrite this as dE is equal to sigma dx dy over 4 pi epsilon naught r squared, like so. Okay. That gives us well, actually, I need to put an r hat over here because I need to get the direction, which is critically the next piece. This would be the whole dE, the dE that points off at an angle like that, but that's not what we want. Oh, as we discussed earlier, we only care about the z component of this. So if we think of, if we draw this here, this would be dE, the z component. So think about this in 3D. There's part of it pointing up. This dE is pointing off at some strange angle, and this we only want the z component of it. I think there being a little right angle there. Okay, to find dEz, the component in the z direction, we can use trigonometry. There's a couple different ways we can do this. My favorite way to do this is similar triangles. So you can, for example, compare this triangle here with this triangle here, and you can say the vertical component of the dE we want, so dE in the z direction is to the h, is to the vertical part here, as the entire dE, the magnitude of dE, is to r. So you can do it via similar triangles. If you don't like doing it via similar triangles, an alternative, so I'll do the alternative method over here. The alternative way of doing this is saying that there's some angle. Let's call this angle, do it in red, theta. We can call that angle up there theta. We would say that dEz is equal to dE times cosine of theta, but and then cosine of theta, because of these two thetas are the same, cosine of theta is h over r, and that gives you the same thing. Either way you do this, you conclude that d, I can put a magnitude there, d E in the z direction is the entire magnitude of dE times h over r. So two different methods. You can use trigonometry or just similar triangles, and you get this thing here. Okay, so we can apply that over here. We have dE, we have the dE vector, we have we can get the component, it's z component now. So doing this, we get dEz is equal to h let's do sigma next, h sigma dx dy over 4 pi epsilon naught r cubed, because we have two r's from here, one r from there, so we get r cubed. Okie dokie. Now let's put in r. So what is r. So let's go back to this thing up here where we're going to try to find the distance from this little charge element to our point of interest. Okay, so you can use three-dimensional Pythagorean theorem where x squared plus y squared plus h squared is equal to r squared. If you don't know three-dimensional Pythagorean theorem, you can do it in two steps. You can say x squared plus y squared is equal to this hypotenuse here squared, and then you can take that squared plus h squared is equal to r squared. Either way, you get r squared is equal to the square root of x squared plus y squared plus h squared. Oops, don't do that. Using that below, so go down here, we'll plug that r, that whole big square root thing into here, and we get that dEz is equal to, and I'm going to leave a suspiciously large gap, h sigma over 4 pi epsilon naught, and then x squared plus y squared plus h squared to the 3 halves. It was cubed and then square rooted, so it gets 3 halves, and then dx dy out here. Why did I write dx dy out there and leave the suspiciously large space over here? It's because I'm going to integrate. I'm going to integrate both sides. So integrate dz, that's just dez, that's just going to give me ez. And I'm going to integrate this side over here as well. So the x integral, actually, let's switch the order. Let's do, no, that's the way I went. That's the way I went. I'm going to do x first. Let's go back, look up here. I'm going to do x first. I'm going to integrate across here first, and then I'm going to integrate the infinite length. Okay, so we have our little dx and dy there. So we're going to integrate across x first. So we're going to integrate that distance first, and then that way. You could do either way. I'm just picking it to do it this order because I am. Okay, so the integral, the inside integral, the dx integral, the inside integral, I'm going to do from minus L over 2 to L over 2. The outside integral, which is dy, I'm going to integrate from minus infinity to infinity. Okay. The integral on the left, dez integrated, just gives you ez. Ez. So ez is equal to this big thing here. So let me just double check my notes. Yeah. So that is I mean, that's the integral. So after this, it's all math. The physics is done. You've gotten it down to an integral. Now we're just, well, 2 integrals. Now we've just got to do some integrals and work things out. Okay. The first step of these integrals, I'm going to pull out some constants. H is a constant, sigma is a constant, 4 pi epsilon naught are all constants. So I can just pull them all out of the integral. And actually, let's leave h in for, yeah, actually, my notes, I left h in, so I'll just do that. So, but I can pull 4 pi epsilon naught out. So ez is equal to 1 over pi epsilon naught, integral from minus infinity to infinity, integral from minus L over 2 to L over 2 of, or sorry, we'll pull the sigma out too. Sigma 2. So now I have h on the top and x squared plus y squared plus h squared to the 3 halves dx dy. Okay, so this is an integral. This is a hard integral. To do this integral, you could look it up. I list how to do some integrals in the top of the homework. You can also look it up in a book. Back in the day, before the internet existed, there was this book called Gradstein-Rizek, which you went to the library and you went up to whatever stacks and you found Gradstein-Rizek and you looked through it. It's this huge tome of a thing that had a bunch of integrals in it. You had to know how to use the index in this thing to find the integral you were looking for. And you found the integral, and That used to be how you do integrals. This is the 21st century. We now use the internet. So you can use you can look these up on Mathematica. Mathematica may be able to do the integral. You can Google it. You can find integral tables on the internet. You can use other programs. I like to use MathCAD, which is based on Maple. But sometimes all of these fancy programs just fail, and you have to go down to the basics and go find Grad-Stein-Rizek and look up your particular integral, and that's it. Okay, for this particular integral, I've already looked it up. I used MathCAD specifically. So when I looked it up, I found that the integral of, let's see, how did I write this? Integral of 1 over x squared plus y squared plus h squared. Remember, when you're looking this up in Grad-Stein-Rizek, they may have, z instead of h, right? They may be using different variables, so you sometimes have to make some changes to get to find the integral you're looking for. But anyway, so that dx happens to be x over y squared over y squared. No, yeah, y squared. Plus h squared, the square root of x squared plus y squared plus h squared plus c, because this is an indefinite integral. Okay, so now what I'm going to do is I'm going to plug, because I have the integral, I'm going to plug in my two limits. I'm going to plug L equals -2 and, or L over L, or sorry, x equals minus L over 2 and x equals plus L over 2. That the subtraction will cause the c to cancel, and I'll get L over 2 divided by a bunch of junk, minus a minus L over 2 divided by the same bunch of junk. And it'll be the same because when you square x, the negative goes away. So the basement is the same. So you see that when you plug this in at their two limits, your minus L over 2 and your L over 2, they basically just add together because you get the minus here. So you get minus L over 2 and or L over 2 and a minus L over 2, which just gives you L over all that junk. So I'm just going to write all that out like that, where I say the resulting is dEz is equal to, same thing, sigma 4 pi epsilon naught. Still have my other integral, minus infinity to infinity, of LH over, and now I have y squared plus h squared, the square root of x became L over 2 squared plus y squared plus h squared dy. Okay, so I made it through one of the integrals. Now I need to make it through the other integral. Okie dokie, how am I going to do that? Well, once again, you look it up on a table or something. So this one's a little more obscure, but you can still find it. And the answer to this is, I'm just going to write it out this time. Ez is equal to sigma. You pull out your L and your H. So LH, they're constants, over 4 pi epsilon naught. You do this integral, and you get that it's 2 over HL times the arctan of y L over 2 H, the square root of L over 2 squared plus y squared plus h squared, evaluated at minus infinity. And we should say what we're which variable goes to minus infinity, since that's kind of ambiguous, at y equals minus infinity and y equals infinity. So I'm going to evaluate that at y equals minus infinity and y equals infinity. Okie dokie. you might think, oh, shoot, I've got infinity. What's going to happen? Well, it actually works out fairly nicely. So if you stick y infinity in for y here and infinity in for y there, so the y in the bottom, this y squared, will dominate the other two terms because it's going to infinity, so the other two terms are irrelevant. So it blows up. You get y squared, square rooted, just gets y, and then it cancels with the y on the top. So it turns out when y goes to infinity, let's write this out, lim the y goes to infinity of y L over 2 of h, the square root of L over 2 squared plus y squared plus h squared. That's an h squared. Despite my bad handwriting, that is in fact an h. That just goes, this whole square root just cancels the y, and you end up with L over 2h. If you put in a negative infinity, then the negative cancels in the bottom, but you get a negative y in the top, so you just get negative L over 2h. So you can stick those two limits in, and you get EZ is equal to sigma LH over 4 pi epsilon naught times, well, actually, before we do that, we can just cancel this LH there. Make my life just a little bit easier. And then I get, so I get 2 times arctan of L over 2h minus a minus, because the when you put in the neg, well, sorry, maybe I'll just do that in 2 steps. Minus 2 arctan of minus L over 2h. Fun fact of arctan, same thing as tan, is that tangent of a minus thing is minus the tangent, so that minus can come out front and make that a plus. Then these two terms are the same. You can add them together. And you get, then that gives you a 4 on the top. That cancels a 4 on the bottom. You get EZ is equal to sigma over pi epsilon naught, the arctan of L over 2h. That, ladies and gentlemen, is the solution. Okay, so that's easy. But as I say, when you get to the solution, you're not done yet. You still have to interpret it. So you would write this down, you would get points for it, but it's important to take some time to think about this solution. So let's remind ourselves of what the original problem was, way back up there. So the original problem is we had this strip of charge, and we were trying to find the field here. And the strip has charge density per unit area of sigma. So if sigma goes to 0, E goes to 0. Sure, if there's no charge, there's no E. If H gets big, meaning you're a long ways away, you get a small thing in the arctangent, which also gives you the arctangent gets small, and then you get 0. That's good. If you're a long ways away, you don't get any charge. If L goes to 0, then you get arctan of 0 gives you 0, and you get E is 0, which means that if you shrink the ribbon width to 0, all the charge goes away, and you're left with no field. Now, an interesting limit you can do is you think, what if I squeezed the ribbon, so I made L smaller, but increased sigma? So instead of keeping sigma the same and making it thinner, what if I kept the total charge the same and just squeezed that charge into a thinner and thinner strip? In that limit, I know that it should, if I squeeze it into a thinner and thinner strip in the middle, basically it would become a line charge. In that case, this answer should reduce to the field of a line charge. So let's try that limit. So we're going to try the limit where we keep the charge per unit length the same. So we have to grow sigma. mathematically, how you do that is you say, well, lambda, the charge per unit length along the strip or length along the line after it becomes a line, is sigma times sigma L, or in other words, sigma is lambda over L, the width of the strip. So if we plug that in, we get EZ is equal to lambda over pi epsilon naught L arctan of L over 2h. Now we can take the limit that L goes small. So lim of L goes to 0 of EZ is equal to lim L goes to 0 of lambda over pi epsilon naught L arctan of L over 2h. Okay, to zoom into my handwriting didn't get so bad. So that quantity is, well, if you could do this limit, one way to do this limit is to use L'Hopital's rule. I'm too lazy to write out L'Hopital's rule, so I'm going to use another rule. The fact that the rule is that arctangent of a small angle, so arctangent of a small quantity is roughly equal to that quantity. There's rule that says for small angles or small values, arctan of small number x is approximately equal to x for small x. If you remember the plot of arctan, arctan looks something like this. So the line in the middle, basically near 0, it just looks like a line. Okay, so if you happen to remember that trick, then you can say in the limit this goes 0, this thing in here becomes small. In fact, it becomes infinitely small. So this works really great. And so we can just say that arctan of this thing just becomes the thing in parentheses, and you get the lim L goes to 0 of EZ is equal to lambda over pi epsilon naught L times L over 2h, where conveniently the L's cancel, and I simply get lambda over 2 pi epsilon naught h. This is a very look-upable answer. This is indeed the charge or the field you would get from an infinite line charge. So this is this here has been a limit test of our solution. Our solution is up here. So with that, have fun on the rest of the homework.